800 million years after the birth of everything after time, space, energy, and matter emerged from an unfathomable singularity, something that defied the laws of cosmic evolution was already lurking in the shadows. Hidden within a faint, distant galaxy, nearly invisible to even our most advanced instruments, lay a black hole so massive it should not have existed at that point in cosmic history. Weighing in at 400 million times the mass of our Sun, this sleeping titan was discovered not by the brilliant light of consumption, but by the subtle gravitational whispers it left in its wake. The James Webb Space Telescope, JWST, stationed a million miles from Earth in serene silence, had just revealed a cosmic anomaly that upends decades of astrophysical theory. Scientists once believed that black holes of such staggering size required billions of years to accumulate their mass through steady feeding. Yet here one sat silent, dormant, and impossibly ancient, challenging everything we thought we knew about how the universe builds its most extreme objects. The discovery occurred not during a search for the extraordinary, but in the routine scanning of the early cosmos. Researchers from the University of Cambridge were analyzing data from the JWST Advanced Deep Extragalactic Survey, a program aimed at charting galaxies that formed during the universe's so-called cosmic dawn. At that epoch, just 800 million years after the Big Bang, the cosmos was still emerging from its primordial fog. The first stars had only recently ignited, and galaxies were small, chaotic, and far from the majestic spirals we see today. In such a young universe, finding any supermassive black hole would be surprising. Finding one of this scale, and in a state of near total dormancy, was nothing short of revolutionary. Unlike the brilliant beacons astronomers usually hunt active galactic nuclei and quasars that blaze across billions of light years, this object emitted almost no light. Black holes typically betray their presence through violence. As gas spirals toward the event horizon at tremendous speeds, friction heats it to millions of degrees, producing light so intense it outshines entire galaxies. But this black hole was fasting. Its accretion disk, if it had one at all, was faint and cold, consuming material at just 2.4% of its theoretical maximum rate. To put that in perspective, it's as if a human ate only one meal per month, instead of 3 a day, barely enough to register. How then did scientists detect it? Through spectroscopy, the art of splitting light into its constituent wavelengths, much like passing sunlight through a prism. By analyzing the motion of gas near the galaxy's center, they found unmistakable signs of something profoundly massive warping the fabric of space-time. Gas was orbiting at thousands of miles per second, a velocity that could only be explained by an object hundreds of millions of times more massive than our Sun. Yet this object produced no significant radiation. It was, for all intents and purposes, invisible except for the gravitational footprint it left on nearby matter. This black hole resides in a galaxy astronomers have catalogued as GNZ 11-1830, or a similar early designation, a modest collection of stars with a total stellar mass of roughly 830 million. Suns tiny compared to the Milky Way's 200 billion. In today's universe, supermassive black holes typically account for about 0.1% of their host galaxy's stellar mass, a ratio that appears finely tuned by billions of years of co-evolution. Feedback from the black hole regulates star formation, and in turn, the galaxy's growth feeds the black hole in a delicate equilibrium. But here, the black hole alone makes up an astonishing 40% of the galaxy's stellar mass. That's 400 times the expected ratio. Imagine a heart weighing 40% of your total body. It would be unsustainable, catastrophic. Yet this system not only exists but persists, continuing to form stars, albeit at a suppressed rate. The implications are profound. If such an object can exist so early in cosmic history, our models of black hole formation must be fundamentally incomplete. Standard theory posits a slow, incremental process. A massive star collapses, leaving behind a black hole of 10 to 100 solar masses. Over eons, it accretes gas or merges with other black holes, growing steadily but never exceeding the Eddington limit, a theoretical ceiling on how fast a black hole can consume matter before radiation pressure blows away the incoming fuel. Named after British astrophysicist Arthur Eddington, this limit acts like a cosmic speed bump. Try to eat too fast, and the resulting glare pushes your food away. According to this model, even if a black hole fed at the Eddington limit continuously for 800 million years, it could only grow to about 100,000 solar masses, nowhere near the observed 400 million. The math simply doesn't work. So either the black hole started much larger than stellar collapse allows, or it grew far faster than conventional physics permits. Both possibilities force us to reconsider long-held assumptions. Lead researcher Roberto Maialino and his team at Cambridge's Cavendish Institute for Cosmology proposed a radical alternative. Black holes don't grow steadily. Instead, they feast in short, violent bursts, episodes of super Eddington, accretion, where they briefly devour matter at 2, 3, or even 5 times the theoretical maximum. These feeding frenzies might last only 5 to 10 million years, a blink in cosmic time, but they allow explosive growth. Afterward, the black hole enters a long dormancy, lasting perhaps 100 million years or more, during which it consumes almost nothing and becomes nearly invisible. This cyclical pattern resembles the behavior of hibernating animals. A grizzly bear spends months gorging before winter, then sleeps for half a year, surviving on stored fat. Similarly, a black hole might binge during rare cosmic feasts, triggered by galaxy mergers, gas instabilities, or dense inflows, then retreat into silence as its larder empties. Crucially, dormancy lasts far longer than activity, 10 to 20 times longer in fact. That means at any given moment, 95% of black holes might be asleep. We've been surveying the universe during dinner hour, mistaking the noisy minority for the whole population. This insight solves a long-standing puzzle. Why do we see so few active black holes in the early universe compared to the number of galaxies? If most are dormant, the discrepancy vanishes. The JWST team found this sleeping giant in a sample of just 35 galaxies, suggesting such objects might be common. Their detection was only possible because of the black hole's enormous mass. Smaller dormant black holes would remain hidden, their gravitational influence too weak to measure with current technology. JWST's infrared capabilities were essential. Light from the early universe is stretched by cosmic expansion, shifting from ultraviolet to infrared by the time it reaches us. Optical telescopes like Hubble can't see these wavelengths clearly, but JWST, cooled to minus 380 degrees F behind a tennis court-sized sunshield, captures this redshifted light with unprecedented sensitivity. Its near-infrared spectrograph dissected the galaxy's light into a detailed spectrum, revealing broad emission lines, smears in the spectral signature caused by gas moving at extreme velocities near an invisible central mass. These lines are the telltale fingerprint of a supermassive black hole, even when dormant. Further analysis showed the galaxy's star formation is unusually low for its era. In the gas-rich early universe, galaxies typically form stars at furious rates. But here, something has throttled that process. The culprit, almost certainly past outbursts from the central black hole. During earlier active phases, its radiation and winds would have heated and expelled gas, preventing it from cooling and collapsing into stars. Even now, in dormancy, the galaxy bears the scars of that violence, a suppressed star formation rate that matches simulations of black hole feedback. This discovery forces a reckoning. If black holes can grow this large this quickly, then either they form from seed black holes far more massive than those left by dying stars, or they routinely violate the Eddington limit in ways we're only beginning to understand. One compelling theory is direct collapse. In pristine regions of the early universe, devoid of heavy elements and bathed in intense radiation, giant gas clouds might collapse directly into black holes of 100 to 1 million solar masses, skipping the star phase entirely. These massive seeds could then grow into the behemoths JWST is now finding. Alternatively, the black hole may have consumed matter in clumpy, chaotic streams that bypassed the usual radiation pressure. In dense, turbulent environments, gas doesn't flow smoothly. It arrives in dense clumps that punch through the outward pressure, delivering mass directly to the event horizon. Simulations show such conditions were common in the early universe, enabling brief super-Eddington growth. Whatever the mechanism, the result is clear. The universe builds its monsters faster and more efficiently than we ever imagined. And if one such dormant giant exists in a tiny survey patch, how many more lie undetected? Statistical models suggest that for every 400 million solar mass black hole we see, there could be dozens at 100 million, hundreds at 10 million, all invisible to current instruments. We are seeing only the tip of an iceberg of sleeping titans. This changes everything. Galaxy evolution models must now account for black holes that dominate their hosts from the very beginning, not as late additions, but as central architects. The feedback from their violent youth shapes star formation, gas dynamics, and chemical enrichment for billions of years. Dormant or not, their legacy endures, and as JWST peers deeper into time toward galaxies that formed just 200 or 300 million years after the Big Bang, we may find even more extreme objects. Perhaps the first black holes were born not from stars, but from the direct collapse of primordial gas, or even from density fluctuations in the infant universe itself. Each new discovery chips away at the old narrative, revealing a cosmos far more dynamic, violent, and mysterious than textbooks once described. For now, one truth stands: in the quiet dark of the early universe, giants sleep, and thanks to humanity's most powerful eye on the sky, we are finally learning to see them, even in their silence. The discovery of this dormant behemoth didn't just challenge assumptions, it shattered a foundational pillar of modern astrophysics, the idea that black holes and galaxies evolve in lockstep through a gentle, feedback-regulated dance. For decades, scientists believed that supermassive black holes were latecomers in cosmic history, growing slowly in tandem with their host galaxies. The black hole's mass was always a tiny fraction, about 1,000th of the galaxy's stellar content, a ratio that seemed carved into the laws of nature by billions of years of mutual influence. But the object JWST uncovered in galaxy GN 10,001,830 turned that narrative inside out. With a mass equivalent to 400 million suns residing in a galaxy whose stars barely totaled 830 million solar masses, the black hole wasn't just a passenger, it was the pilot, the architect, perhaps even the origin point. This imbalance wasn't a statistical fluke. It was a declaration that the early universe operated by different rules, governed by processes far more violent and efficient than previously imagined. The real shock came not from its size alone, but from the silence that accompanied it. In a cosmos where black holes are usually spotted by their luminous fury quasars blazing across billions of light years like lighthouses in a storm, this one offered no such spectacle. It was fasting, consuming matter at a mere 2–4% of its theoretical maximum intake. To detect it required not the blinding glare of an accretion disk, but the subtle gravitational tremors it imprinted on nearby gas. Using JWST's near-infrared spectrograph, researchers dissected the galaxy's light into a high-resolution spectrum. Within that spectral tapestry, they found hydrogen emission lines broadened far beyond normal. These weren't sharp, calm signatures, they were smeared, stretched across wavelengths, indicating gas whipping around an invisible center at speeds exceeding thousands of miles per second. Only an object of staggering mass could exert such gravitational control, and yet there was almost no accompanying radiation. The paradox was complete. Something enormous, ancient, and utterly quiet had been hiding in plain sight. This paradox forced a radical rethinking of black hole life cycles. For years, models assumed steady growth, black holes accreting gas at or near the Eddington limit, a threshold where radiation pressure from infalling matter balances gravitational pull. Exceed this, and the black hole's own brilliance pushes away its food supply. But such a model couldn't explain how a 400 million solar mass object formed less than a billion years after the Big Bang. Even if it fed non-stop at the Eddington rate from the moment the first stars died, it would only reach about 100 solar masses, nowhere near the observed size. The math was unambiguous. Either the black hole began life far larger than stellar remnants allow, or it grew in ways that defied standard accretion theory. Roberto Maialino and his team at Cambridge proposed the latter. Black holes don't graze, they binge. They enter brief, cataclysmic feeding frenzies episodes where accretion surges to 2, 3, or even 5 times the Eddington limit, followed by long stretches of near-total dormancy. These bursts might last only 5 to 10 million years, but in that time a black hole could double or triple its mass. Then, having blown away its gas reservoir with radiation and winds, it goes quiet for 100 million years or more. This cycle mirrors biological hibernation: feast intensely, then sleep through the scarcity, and crucially, the sleeping phase lasts 10 to 20 times longer than the active one. That means at any random moment in cosmic history, upwards of 95% of black holes are likely dormant silent giants invisible to traditional surveys that hunt only for brilliance. This insight reframes everything. For decades, astronomers counted active black holes and assumed they represented the norm. Finding relatively few in the early universe seemed puzzling. Why weren't more galaxies lit up by quasars? The answer may be simple. Most black holes were simply asleep. The Cambridge team's detection of a single dormant giant in a sample of just 35 galaxies suggests these objects are far more common than previously thought. If such a monster could be found so easily in a tiny patch of sky, how many others lie just beyond our current sensitivity? The implications ripple outward. Galaxy evolution models that assumed continuous black hole feedback must now incorporate intermittent, explosive episodes. Star formation isn't gently throttled. It's violently interrupted, then allowed to resume during quiet phases. Galaxies don't grow smoothly, they pulse, alternating between bursts of stellar birth and long stretches of quiescence, all orchestrated by the central black hole's feeding rhythm. And the host galaxy itself bore the scars of this violent past. Despite existing in the gas-rich early universe, a time when galaxies typically form stars at furious rates, GN 10,001,830 showed suppressed star formation. Its spectrum revealed weak ultraviolet emission from young, hot stars, indicating star birth was occurring, but at a fraction of the expected pace. The culprit almost certainly past outbursts from the central black hole. During earlier active phases, its intense radiation and high-velocity winds would have heated the galaxy's interstellar gas to millions of degrees, preventing it from cooling and fragmenting into new stars. Even now in dormancy, the gas remains hot, and the star formation rate stays low. The galaxy is in recovery, not dead, but healing from a cosmic wound inflicted by its own heart. This delayed effect demonstrates that black hole feedback isn't just a momentary event. It's a legacy that shapes a galaxy's evolution for tens or even hundreds of millions of years after the black hole goes quiet. Detecting such an object required more than luck. It demanded technological revolution. The James Webb Space Telescope was uniquely equipped for this task. Positioned at the L2 Lagrange point, a million miles from Earth, it operates in profound cold behind a tennis court-sized sunshield that blocks heat from the Sun, Earth, and Moon. This allows its instruments to detect faint infrared signals without interference from their own thermal noise. Crucially, JWST observes in infrared because light from the early universe is stretched by cosmic expansion, shifting from ultraviolet and visible wavelengths into the infrared part of the spectrum. Hubble, optimized for visible light, could barely glimpse these distant galaxies. JWST sees them clearly. Its 5-meter gold-coated beryllium mirror, more than 6 times larger in collecting area than Hubble's, gathers enough photons from these faint, ancient sources to enable detailed spectroscopy. Without this capability, the dormant black hole would have remained invisible, its gravitational influence too subtle to detect against the background noise of stellar light. The team used a technique called spectral decomposition to isolate the black hole's faint signature. By comparing the central region of the galaxy to its outer regions, they identified emission features unique to the core broadened hydrogen lines indicating high-velocity gas motion, consistent only with a supermassive black hole. They also employed multiple narrowband filters to highlight specific wavelengths where accretion disk emission peaks, then subtracted images to reveal the spatial concentration of light at the galaxy's center. Every method converged on the same conclusion: a massive, dormant black hole was present. Computer simulations further confirmed the finding. Thousands of models were run, varying black hole mass, accretion rate, and galaxy properties. Only scenarios involving a tilde 400 million solar mass black hole feeding at minimal rates reproduced the observed spectrum. Alternative explanations, such as a dense star cluster or unusual stellar population, were ruled out. The velocity dispersion of the gas was simply too high. No collection of stars could produce such gravitational pull without collapsing into a black hole. This leads to the most unsettling implication. If one such object exists in a small survey, the early universe may be teeming with them. Statistical extrapolation suggests that for every massive dormant black hole we can detect, there are dozens or even hundreds of smaller ones below our current detection threshold. Black hole mass distributions follow a steep power law. Smaller black holes are vastly more numerous than larger ones. If the 400 million solar mass behemoth is the tip of the iceberg, the submerged bulk consists of countless 10 million or 50 million solar mass dormant black holes, all invisible to current instruments. We are not just missing a few outliers, we are blind to the majority of the population. This means our understanding of cosmic structure is built on a partial census, one that sees only the most extreme, active, or massive examples, while the quiet majority remains hidden. And this hidden population could reshape our maps of the universe. Modern cosmology relies on catalogs of galaxies to reconstruct the cosmic web. the vast filaments and voids that define large-scale structure. But if nearly every early galaxy hosts a supermassive black hole, most of them dormant, then our maps are missing a critical component. These black holes contribute significant gravitational mass without emitting light. While dark matter dominates the unseen mass budget, dormant black holes could still influence local dynamics, altering how galaxies orbit within clusters, how gas flows between systems, how mergers unfold. Their cumulative effect may be small compared to dark matter, but not negligible, especially in dense regions where black hole concentrations are high. More importantly, their feedback history, those past bursts of activity, would have heated gas, suppressed star formation, and altered chemical enrichment across entire protogalactic clouds. Galaxies we see today may owe their shapes, sizes, and stellar populations to black holes we never observed. This brings us to the question of origins. How did such a massive black hole form so quickly? One possibility is direct collapse. In the pristine conditions of the early universe, where gas contained almost no heavy elements and was bathed in intense ultraviolet radiation from the first stars, massive clouds of hydrogen and helium might have collapsed directly into black holes of 100 0 to 1 million solar masses, skipping the stellar phase entirely. These seed black holes would then serve as ready-made foundations for rapid growth. Another theory invokes primordial black holes, hypothetical objects formed in the first instance after the Big Bang from density fluctuations in the hot plasma. Though never confirmed, such objects could have provided massive seeds. A third path combines moderate seeds with super-Eddington accretion. Even a 10-0 solar mass black hole formed from a dense star cluster collapse could reach 400 million solar masses in under a billion years if it experienced multiple feeding bursts. Simulations increasingly support the burst model. When researchers program gas dynamics to allow temporary violations of the Eddington limit, through mechanisms like optically thick inflows, magnetic funneling, or clumpy accretion, the resulting black holes match observations. In dense, turbulent early universe environments, gas doesn't flow smoothly. It arrives in chaotic streams and clumps that can overwhelm radiation pressure, delivering mass directly to the event horizon. These episodes are self-limiting. After a few million years, the black hole's own energy output clears its surroundings, shutting off the supply and triggering dormancy. This cycle then repeats with the next influx of gas, perhaps from a galaxy merger or a collapsing filament of the cosmic web. Galaxy mergers were far more common in the early universe, when structures were closer together and gravitational interactions more frequent. A collision between two gas-rich galaxies could funnel enormous amounts of material toward their central black holes, triggering simultaneous feeding frenzies. If the black holes eventually merged, the resulting object would inherit the combined mass and angular momentum, potentially spinning fast enough to further enhance accretion efficiency. This scenario could explain not only the rapid growth, but also the extreme mass-to-galaxy ratios. The black hole grew explosively before the merged galaxy had time to reorganize its stars and gas. Whatever the mechanism, one thing is clear: the universe had tools to build monsters far earlier than we thought possible. And JWST is just beginning to reveal them. As deeper surveys probe galaxies that formed only 200 to 400 million years after the Big Bang, we may find even more extreme objects, black holes that formed before their galaxies, seeds from the cosmic dawn, or relics of physics beyond the standard model. Each discovery chips away at the old narrative of gradual, orderly growth, replacing it with a vision of a violent, dynamic youth where black holes weren't just inhabitants of galaxies. They were their creators, their destroyers, and their hidden rulers, We are learning to see the invisible, not by waiting for light, but by listening to gravity's whisper. And in that silence, the universe speaks volumes. The implications of finding a dormant black hole, so massive and so early, stretch far beyond a single anomalous galaxy. They ripple through the entire framework of modern cosmology. For decades, astronomers have assumed that the coevolution of galaxies and their central black holes followed a gentle, self-regulating feedback loop. In this model, black holes grow slowly as their galaxies form stars, and in turn, the energy they emit during active phases gently suppresses further star formation, maintaining a cosmic balance. The ratio of black hole mass to stellar mass, roughly 0.1%, was treated almost like a law of nature, observed consistently across thousands of galaxies in the local universe. But the discovery of a black hole that constitutes 40% of its host galaxy's stellar content shatters that assumption. It reveals a universe where balance is not the rule but the exception, a cosmos that, in its youth, operated with chaotic intensity, where black holes could dominate their environments from the very beginning, long before equilibrium had a chance to emerge. This forces a fundamental reassessment. Perhaps galaxies don't shape black holes so much as black holes shape galaxies, and they've been doing so since the first flickers of light in the cosmic dawn. The host galaxy, GN 10,001,830, is itself a quiet enigma. Small, faint, and unremarkable at first glance, it contains only about 830 million solar masses and stars, less than 1% of the Milky Way's stellar content. Yet within this modest system lies a gravitational titan so massive it warps the motion of gas at velocities exceeding thousands of miles per second. The galaxy's star formation rate is also unusually low for its epoch. In the gas-rich early universe, most galaxies of similar size were stellar nurseries, churning out new stars at furious rates. GN 10,001,830, by contrast, appears subdued, almost exhausted. Spectroscopic analysis reveals weak ultraviolet emission lines, signatures of hot, young stars, but their intensity is muted, suggesting star birth is occurring at only a fraction of the expected pace. The most plausible explanation: past outbursts from its central black hole. During earlier feeding frenzies, the black hole would have unleashed torrents of radiation and high-velocity winds, heating the interstellar medium to millions of degrees and preventing gas from cooling and collapsing into stars. Even now, in dormancy, the galaxy bears the thermodynamic scars of that violence. The gas remains too hot to efficiently form stars, trapped in a prolonged recovery phase. This delayed feedback demonstrates that black hole influence is not instantaneous, but cumulative, its effects echoing through cosmic time long after the black hole has fallen silent. This pattern of episodic violence followed by extended quiescence offers a compelling explanation for another long-standing puzzle: the apparent scarcity of active black holes in the early universe. Traditional surveys, designed to detect luminous quasars and active galactic nuclei, consistently found fewer such objects than models predicted. If every galaxy hosts a central black hole, and all evidence suggests they do, then why aren't more of them glowing? The answer may lie not in their absence, but in their behavior. If black holes spend 95% of their lives in a dormant state, as the binge-and sleep model suggests, then the visible population represents only a tiny, transient fraction of the total. We've been conducting a census during the brief moments when black holes are active, mistaking the exception for the norm. The detection of a single dormant giant in a sample of just 35 galaxies strongly implies that such objects are common, perhaps even ubiquitous in the early cosmos. And if 1/400 million solar mass behemoth can be found so easily, how many smaller, equally dormant black holes remain hidden below our current detection thresholds? This raises profound questions about the completeness of our cosmic maps. Every atlas of the distant universe is built from light. Galaxies are plotted based on their emitted radiation, their masses inferred from stellar populations, their evolutionary states deduced from color and spectral features, but dormant black holes emit almost no light. They are gravitational ghosts, detectable only through their subtle influence on nearby matter. As a result, they are entirely absent from conventional galaxy catalogs, despite potentially contributing significant mass and shaping galactic evolution through past feedback. Imagine trying to understand Earth's climate by only measuring sunlight and ignoring the oceans. The oceans don't glow, but they store heat, drive weather patterns, and regulate temperature over centuries. Similarly, dormant black holes may be the hidden reservoirs of cosmic influence, silent today, but having sculpted the galaxies we see through ancient eruptions of energy. The technological feat that made this discovery possible cannot be overstated. The James Webb Space Telescope was uniquely suited to this challenge. Operating 1,000,000 miles from Earth at the L2 Lagrange point, it maintains a stable thermal environment behind a tennis court-sized sunshield that blocks heat from the Sun, Earth, and Moon. This allows its instruments to cool to -380 degrees F, minimizing internal infrared noise that would otherwise drown out faint cosmic signals. JWST's 6.5-meter gold-coated beryllium mirror, more than 6 times larger in collecting area than Hubble's, gathers precious photons from objects so distant their light has been stretched from ultraviolet into the infrared by the expansion of the universe. Without this infrared sensitivity, galaxies from the cosmic dawn would remain shrouded in cosmic redshift, invisible to optical telescopes. But JWST doesn't just see them, it dissects them. Using its near-infrared spectrograph, researchers split the faint light of GN 10,001,830 into a high-resolution spectrum, revealing the telltale signatures of gas orbiting an invisible central mass. The broadening of hydrogen emission lines smearing across wavelengths due to Doppler shifts from high-velocity motion provided unambiguous evidence of a supermassive black hole. Alternative explanations, such as dense star clusters or unusual stellar populations, were ruled out through extensive computer modeling. No collection of stars could produce such extreme velocities without collapsing into a black hole under its own gravity. Yet even with JWST's power, the detection was only possible because of the black hole's extraordinary mass. Smaller dormant black holes, those below 100 million solar masses, would produce weaker gravitational signatures, their spectral broadening faint and easily lost in the noise of stellar light. Statistical models based on black hole mass distributions suggest that for every object like this, there could be dozens at 50 million solar masses and hundreds at 10 million. The vast majority of the dormant population remains invisible, not because it doesn't exist, but because our eyes aren't sharp enough to see it. This hidden majority may hold the key to understanding how galaxies truly evolved. If nearly every early galaxy hosted a supermassive black hole, most of them sleeping, then feedback from black hole activity was not a rare occurrence, but a universal process, shaping star formation, gas dynamics, and chemical enrichment across the entire infant universe. This leads directly to the question of origins. How could such a massive black hole form so quickly after the Big Bang? Standard theory posits that black holes begin as the collapsed cores of massive stars, yielding remnants of 10 to 100 solar masses. From there, they grow through accretion and mergers, constrained by the Eddington limit, the theoretical maximum rate at which they can consume matter before radiation pressure blows away the incoming fuel. But even under ideal conditions, this process cannot produce a 400 million solar mass object in less than a billion years. The math simply doesn't add up. This forces us to consider more radical possibilities. One compelling theory is direct collapse. In pristine regions of the early universe, devoid of heavy elements and bathed in intense ultraviolet radiation from nearby galaxies, giant clouds of hydrogen and helium might have collapsed directly into black holes of 100 to 1 million solar masses, skipping the stellar phase entirely. These massive seeds would then provide a head start, allowing rapid growth through subsequent accretion. Simulations show that such conditions were not only possible, but likely in pockets of the early cosmos, where gas remained hot enough to avoid fragmentation into individual stars. Another possibility involves primordial black holes, hypothetical objects formed in the first fractions of a second after the Big Bang from density fluctuations in the hot, dense plasma of the early universe. If such black holes existed with masses in the millions of solar masses, they could serve as ready-made seeds for the supermassive black holes we observe. Though never confirmed, this idea remains viable, especially as conventional models continue to struggle with the timeline problem. A third path combines moderate seeds with extreme accretion. Even a 10-0 solar mass black hole formed from the collapse of a dense star cluster could reach 400 million solar masses in under 8 billion years if it experienced multiple episodes of super-Eddington feeding. Recent simulations support this scenario, showing that in the turbulent, gas-rich environments of early galaxies, accretion can temporarily exceed the Eddington limit through mechanisms like optically thick inflows, magnetic funneling, or clumpy gas streams that punch through radiation pressure. These feeding bursts are not sustainable. They last only 5 to 10 million years before the black hole's own energy output clears its surroundings, shutting off the supply and triggering dormancy. But during that brief window, growth is explosive. A black hole feeding at 5 times the Eddington limit can double its mass in as little as 10 million years. Multiple such episodes, separated by 100 million year naps, could easily build a behemoth like the one JWST discovered. This cyclical model not only explains the mass, but also the dormancy. The black hole isn't broken or anomalous. It's simply in its natural resting phase, having recently completed a feast. And this behavior aligns with observations of the host galaxy itself, which shows signs of episodic star formation, bursts of stellar birth, followed by long quiet periods, mirroring the proposed rhythm of black hole activity. It's as if the galaxy and its black hole are breathing in sync, inhaling gas, exhaling energy, then resting before the next cycle begins. This revised timeline appends textbook narratives. Instead of black holes as late additions to galactic ecosystems, they may have been foundational architects from the very beginning. In some scenarios, the black hole formed before the galaxy itself, its immense gravity acting as a gravitational seed around which gas and stars would later coalesce. This black hole first model explains the extreme mass ratio. The black hole wasn't growing in tandem with its host. It was waiting for the host to catch up. Such a reversal of roles has profound consequences. It suggests that the properties of early galaxies, their sizes, shapes, star formation histories, were not determined solely by dark matter halos and gas dynamics, but were actively sculpted by the presence of a pre-existing central black hole. Feedback from even brief active phases could have regulated or even halted star formation before the galaxy had fully assembled. imprinting its influence on cosmic structures that would persist for billions of years. And as JWST continues its survey of the deep universe, probing galaxies that formed just 200 to 400 million years after the Big Bang, the stage is set for even more revolutionary discoveries. If direct collapse was common, we may find black holes that are not just massive, but primordial objects that witnessed the birth of the first stars and helped shape the cosmic dawn itself. Each new detection will test these competing theories, refining our understanding of how the universe built its most extreme objects. But one truth is already clear: the cosmos is far more dynamic, violent, and mysterious than we ever imagined. And in its darkest, quietest corners, giants sleep, waiting for the next feast, the next eruption, the next revelation. The discovery of this dormant black hole didn't just expose a gap in theory, it revealed a fundamental flaw in how we've interpreted cosmic silence. For generations, astronomers equated visibility with significance. Bright quasars, blazing accretion disks, and luminous active galactic nuclei were treated as the standard manifestations of black hole existence. Quiet galaxies were assumed to host quiet, modest black holes, perhaps still growing, perhaps starved of fuel, but never colossal. The detection of a 400 million solar mass black hole feigning dormancy in a galaxy barely larger than a cosmic speck shattered that assumption. It forced the realization that silence in the cosmos isn't absence, it's concealment. And the universe may be teeming with invisible titans, their gravitational influence shaping galaxies while their light remains buried beneath the noise of stellar emissions. This reinterpretation has cascading consequences, not only for black hole demographics, but for how we reconstruct the timeline of cosmic evolution itself. One of the most unsettling implications is statistical. The Cambridge team found this black hole in a sample of just 35 galaxies from the JWST survey, a tiny window into the early universe. The fact that such an extreme object surfaced so readily suggests that massive dormant black holes are not rare anomalies, but common fixtures of the primordial cosmos. If one can be found in such a small dataset, how many more lie undetected just beyond our current sensitivity? The answer hinges on the mass distribution of black holes, which follows a steep power law. For every object of mass m, there are typically several to dozens of objects at m/2. Applied recursively, this means that while 400 million solar mass black holes are scarce, 100 million solar mass ones are far more numerous, and 10 million solar mass dormant black holes likely outnumber them by orders of magnitude. Yet current technology, no matter how advanced, can only detect the most massive dormant black holes. Their extreme gravity produces measurable Doppler broadening in gas emission lines, allowing indirect detection through spectroscopy. Smaller black holes warp spacetime too weakly. Their influence drowns in the thermal and rotational noise of their host galaxies. Thus, our census of early black holes is not merely incomplete, it's profoundly biased toward the heaviest outliers. We're counting only the giants, mistaking them for the norm, while the true population remains hidden in darkness. This bias distorts every model built on black hole demographics. Galaxy evolution simulations rely on assumptions about how frequently black holes form, how massive they are at birth, and how they grow over time. If those assumptions are drawn from a skewed sample representing massive, active, or unusually luminous objects, then the models themselves are flawed. For decades, simulations assumed that black holes began as stellar remnants of 10⁻⁰ solar masses and grew steadily, regulated by the Eddington limit. These models successfully reproduced local universe observations, but consistently underproduced massive black holes in the early cosmos. JWST's findings now explain why. The seed population wasn't small, and the growth wasn't steady. Instead, massive seeds, perhaps from direct collapse, combined with episodic super-Eddington accretion to build behemoths long before traditional timelines allowed. Simulations, updated to include these mechanisms, now align with observations. They produce black holes of 400 million solar masses by 800 million years after the Big Bang, matching the mass, dormancy state, and host galaxy properties of GN 10,001,830. Crucially, they also predict that 95% of black holes should be dormant at any given time, a ratio that explains the historical scarcity of active quasars in deep field surveys. The universe isn't lacking black holes, it's full of sleeping ones, and dormancy isn't passive, it's the aftermath of violence. The suppressed star formation in GN 10,001,830 is not a coincidence, it's a fossil record of past black hole activity. During earlier feeding frenzies, the central black hole would have unleashed torrents of radiation and relativistic winds, heating the galaxy's interstellar medium to millions of degrees. At such temperatures, gas cannot cool and fragment into stars. The entire reservoir of star-forming material was effectively sterilized. Even now, in dormancy, the gas remains hot, and star birth proceeds sluggishly. This delayed feedback demonstrates that black holes shape galaxies not through continuous influence, but through episodic catastrophes. A single 5 million year feeding burst can quench star formation for 100 million years or more. The galaxy doesn't live. With its black hole, it endures it, recovering in the quiet intervals between eruptions. This punctuated equilibrium pattern aligns with spectroscopic evidence showing that GN 10,001,830 formed most of its stars in short, intense episodes, likely timed to the black hole's rest periods. The rhythm is cosmic: feed, suppress, sleep, recover, repeat. And in the early universe, where gas was abundant and mergers frequent, these cycles may have repeated multiple times, each burst adding mass to the black hole while throttling the galaxy's growth. The host galaxy's tiny size, just 830 million solar masses in stars, makes this dominance all the more extraordinary. In mature galaxies like the Milky Way, the central black hole accounts for roughly 0.1% of the stellar mass. Here, the ratio is inverted. The black hole outweighs the stars by nearly half. This imbalance suggests the black hole didn't grow alongside the galaxy, it may have preceded it. One compelling scenario is black hole first formation via direct collapse. In pristine regions of the early universe, devoid of heavy elements and bathed in intense ultraviolet radiation from neighboring galaxies, massive clouds of hydrogen and helium could have collapsed directly into black holes of 100 zeros, 0 to 1 million solar masses, skipping star formation entirely. These massive seeds would then act as gravitational anchors, pulling in surrounding gas that would later form stars. In such a model, the black hole isn't a product of the galaxy, it's the seed from which the galaxy crystallizes. The extreme mass ratio isn't a violation of physics, it's a snapshot of a transitional phase caught before the galaxy had time to catch up. Over billions of years, continued star formation and mergers would dilute the ratio, bringing it in line with modern values. But at 800 million years post-Big Bang, equilibrium hadn't been reached, only domination. Another possibility is that the galaxy was stripped. Perhaps GN 10,001,830 was once part of a much larger system. its outer stars and gas torn away by gravitational tides during a close encounter with a neighboring galaxy. The central black hole, bound tightly to the core, would remain intact, while the stellar envelope was shredded and dispersed. What we see today could be the remnant nucleus of a once massive galaxy, its black hole-to-star ratio artificially inflated by loss, not overgrowth. Testing this requires mapping the galaxy's dark matter halo via gravitational lensing. If the halo is unusually massive for the visible galaxy, stripping is likely. If the halo is compact and dense, direct collapse gains support. Either way, the observation challenges the dogma that black hole and galaxy masses are locked in a universal ratio from birth. Instead, the relationship is dynamic, chaotic, and context-dependent, shaped by environment, merger history, and the timing of black hole activation. JWST's role in this revelation cannot be overstated. Its infrared vision was essential not just for seeing redshifted light, but for piercing the dusty veils that shroud early galaxies. Optical telescopes like Hubble struggle to observe galaxies from the cosmic dawn because their light is both redshifted into the infrared and obscured by interstellar dust. JWST's gold-coated beryllium mirror, cooled to near absolute zero behind a tennis court-sized sunshield, captures faint infrared photons with unprecedented clarity. But detection required more than raw sensitivity. It demanded precision spectroscopy. By splitting the galaxy's light into a detailed spectrum, researchers isolated broad hydrogen emission lines from the core, smears in the data caused by gas orbiting at thousands of miles per second. Only a supermassive black hole could produce such velocities. Crucially, the accretion disk was faint, confirming dormancy. The team cross-validated this with imaging filters that highlighted the spatial concentration of emission at the galactic center, ruling out alternative explanations like star clusters or supernova remnants. Every method converged on the same conclusion: a dormant giant hidden in plain sight. Yet even JWST has limits. Its detection threshold for dormant black holes in the early universe is around 100 million solar masses. Below that, gravitational signatures are too weak. That means for every GN 10,001,830 we see, dozens or hundreds of smaller dormant black holes remain invisible. And this invisibility has profound consequences for cosmic cartography. Every map of the early universe is built from light galaxies, are plotted based on stellar emission, their masses inferred from brightness, their evolution deduced from color and spectral features. Dormant black holes contribute zero light but significant gravity. They are absent from these maps, despite potentially regulating the galaxies we do see. Imagine reconstructing Earth's weather patterns while ignoring oceans. They don't glow, but they store heat, drive currents, and shape climate for centuries. Similarly, dormant black holes may be the hidden regulators of cosmic evolution, their past eruptions dictating where and when stars could form across entire protogalactic clouds. This hidden influence extends to large-scale structure, galaxy clusters. The universe's most massive gravitationally bound systems often host central black holes weighing billions of solar masses. Simulations suggest these behemoths began as early giants like the one JWST found. Over billions of years, their host galaxies merged repeatedly, each collision funneling gas to the center and adding black hole mass through mergers. The early head start mattered. A 400 million solar mass black hole at cosmic dawn would dominate merger dynamics, cannibalizing smaller black holes and growing into the cluster's central engine. Its feedback history, those past bursts of activity would have heated intracluster gas, preventing excessive star formation and explaining why modern clusters contain vast reservoirs of hot X-ray emitting gas but relatively few stars. Thus, the dormant giant isn't just an oddity, it's a progenitor. It represents the seed of a future cosmic metropolis, observed during its quiet genesis. Looking forward, the next frontier is gravitational waves. While electromagnetic observations reveal black holes through their interaction with matter, gravitational wave detectors like the future LISA mission will sense them through spacetime ripples from mergers. If massive black holes were common in the early universe, as JWST's findings imply, then merger rates during the first billion years were far higher than previously modeled. LISA could detect dozens of these early collisions per year, providing independent confirmation of the burst-growth paradigm. Each detection would carry information about black hole masses and spins, allowing us to reconstruct the population's evolution directly. Combined with JWST's snapshots of dormant giants, gravitational wave astronomy could finally give us a complete census revealing not just the visible giants, but the hidden multitude that shaped the cosmos from the shadows. For now, one truth endures: the universe is far less luminous and far more massive than we once believed. In its darkest epochs, giants sleep, and thanks to a golden mirror a million miles from home, we are learning to see them in their silence. The detection of this dormant black hole has not only appended theoretical models, it has exposed a critical blind spot in how we observe and interpret the architecture of the cosmos. For decades, astronomers constructed maps of the universe using light as their sole guide. Galaxies were catalogued by their brightness, their mass inferred from stellar populations, their evolutionary state deduced from color and spectral features. But dormant black holes emit almost no light. They are gravitational phantoms, massive, influential, and entirely absent from conventional cosmic atlases. The discovery of a 400 million solar mass black hole lurking in a faint, unremarkable galaxy forces us to confront a disturbing truth. Our picture of the early universe is built on a biased sample, one that sees only the luminous minority while the silent majority remains hidden. This omission is not trivial. It distorts every model of galaxy formation, black hole demographics, and large-scale structure that relies on observed galaxy populations. If nearly every early galaxy hosted a supermassive black hole, and most were dormant, then the feedback shaping cosmic evolution came not from the rare beacons we've tracked, but from countless invisible titans whose past eruptions quietly dictated where stars could form and how galaxies would grow. This hidden feedback is etched into the galaxy GN 10,001,830 itself. Despite existing in an era when the universe was flooded with gas and young galaxies were stellar factories, this system forms stars at a markedly suppressed rate. Spectroscopic analysis reveals weak ultraviolet emission from hot, young stars, evidence that star birth is occurring, but at a fraction of the expected pace. The most plausible explanation lies in the galaxy's recent past. During an earlier feeding frenzy, the central black hole unleashed torrents of radiation and high-velocity winds that heated the interstellar medium to millions of degrees. At such temperatures, gas cannot cool and fragment into stars. The entire reservoir of star-forming material was effectively sterilized. Even now, in dormancy, the gas remains too hot to efficiently collapse. The galaxy is in recovery, not dead, but healing from a cosmic wound inflicted by its own heart. This delayed effect demonstrates that black hole influence is not instantaneous but cumulative, echoing through tens or even hundreds of millions of years after the black hole has fallen silent. The scars of past violence persist, shaping the galaxy's destiny long after the storm has passed. The cyclical nature of this relationship, feast, suppress, sleep, recover, suggests a cosmic rhythm that may be universal in the early universe. Simulations incorporating burst accretion show galaxies experiencing punctuated equilibrium, long periods of quiescence interrupted by brief, violent episodes of black hole activity. During active phases, star formation plummets as feedback heats and expels gas. During dormancy, gas slowly cools and star birth resumes, only to be throttled again when the black hole awakens. This push-pull dynamic explains why GN 10,001,830 star formation history appears episodic, with bursts of stellar birth separated by extended lulls. The galaxy and its black hole are not independent actors. They are locked in a dance of mutual regulation, where one's activity dictates the other's potential. And this dance was likely faster, more chaotic, and more extreme in the early universe, where gas was abundant, galaxies were small, and mergers were frequent. Galaxy mergers were a key driver of this chaos. In the dense, compact universe of 800 million years after the Big Bang, galaxies were closer together and gravitational encounters far more common. When two gas-rich systems collided, their central black holes would be funneled toward the merger remnant's core, surrounded by a deluge of fresh fuel. This sudden influx could trigger a super-Eddington feeding frenzy, allowing explosive growth in just 5 to 10 million years. If the black holes eventually merged, the resulting object would inherit their combined mass and spin, potentially enhancing future accretion efficiency. This scenario not only explains rapid growth, but also the extreme black hole to galaxy mass ratio. The black hole grew explosively before the merged galaxy had time to reorganize its stars and gas into a balanced structure. The system we observe may be caught in this transitional phase, a galaxy still assembling while its black hole has already reached maturity. Yet, even without mergers, the early universe provided ideal conditions for burst growth. Gas clouds were denser, more turbulent, and metal-poor, devoid of heavy elements that cool gas and promote fragmentation into stars. In such environments, accretion could proceed through mechanisms that temporarily bypass the Eddington limit. Clumpy inflows, where dense gas fragments punch through radiation pressure, optically thick flows, where trapped photons fail to push back on infalling matter, and magnetically channeled streams, which funnel material directly to the event horizon, all enable brief super-Eddington episodes. Simulations confirm that these processes were not only possible, but likely common in primordial galaxies. The result, black holes that grew in violent fits and starts, spending most of their lives dormant, invisible, and undetectable. This behavioral pattern solves a long-standing mystery, the apparent underabundance of active black holes in deep field surveys. If black holes spent their entire lives glowing like quasars, we should see far more of them in the early universe. Instead, traditional surveys found relatively few compared to the number of galaxies that should host them. The math never balanced until we realized we were counting only the wrong moments. If dormancy lasts 10 to 20 times longer than active feeding, then, at any random instant, 90–95% of black holes are asleep. We've been conducting a cosmic census during dinner hour, mistaking the feeding minority for the norm. The discovery of a single dormant giant in a sample of just 35 galaxies strongly implies that such objects are common. And if 1/400 million solar mass black hole can be found so easily, how many smaller, equally dormant ones remain hidden below our detection threshold? This hidden population is vast, Black hole mass distributions follow a steep power law. For every object of mass m, there are typically several to dozens at m/2. Applied recursively, this means that while 400 million solar mass black holes are rare, 100 million solar mass ones are far more numerous, and 10 million solar mass dormant black holes likely outnumber them by orders of magnitude, yet current technology, no matter how advanced, can only detect the most massive dormant black holes. Their extreme gravity produces measurable Doppler broadening in gas emission lines, allowing indirect detection through spectroscopy. Smaller black holes warp spacetime too weakly. Their influence drowns in the thermal and rotational noise of their host galaxies. Thus, our census is not just incomplete, it's profoundly skewed. We're counting only the giants, mistaking them for the norm, while the true population remains buried in darkness. This bias infiltrates every layer of cosmological modeling. Galaxy evolution simulations that assume continuous Eddington limited growth consistently underproduce massive black holes in the early universe. But when updated to include massive seeds and episodic super-Eddington accretion, they align perfectly with observations. They produce black holes of 400 million solar masses by 800 million years after the Big Bang, matching the mass, dormancy state, and host galaxy properties of GN 10,001,830. Crucially, they also predict that 95% of black holes should be dormant at any given time, a ratio that explains the historical scarcity of active quasars. The universe isn't lacking black holes, it's saturated with sleeping ones, and this saturation reshapes our understanding of cosmic structure. Modern galaxy clusters, the universe's most massive gravitationally bound systems, often host central black holes weighing billions of solar masses. Simulations suggest these behemoths began as early giants like the one JWST found. Over billions of years, their host galaxies merged repeatedly, each collision funneling gas to the center and adding black hole mass through mergers. The early head start mattered. A 400 million solar mass black hole at cosmic dawn would dominate merger dynamics, cannibalizing smaller black holes and growing into the cluster's central engine. Its feedback history, those past bursts of activity would have heated intracluster gas, preventing excessive star formation and explaining why modern clusters contain vast reservoirs of hot X-ray emitting gas but relatively few stars. Thus, the dormant giant isn't just an oddity, it's a progenitor. It represents the seed of a future cosmic metropolis, observed during its quiet genesis. Looking forward, the next frontier isn't light, it's gravity itself. While electromagnetic observations reveal black holes through their interaction with matter, gravitational wave detectors like the future LISA mission will sense them through ripples in spacetime. From mergers, if massive black holes were common in the early universe, as JWST's findings imply, then merger rates during the first billion years were far higher than previously modeled. LISA could detect dozens of these early collisions per year, providing independent confirmation of the burst growth paradigm. Each detection would carry information about black hole masses and spins, allowing us to reconstruct the population's evolution directly. Combined with JWST's snapshots of dormant giants, gravitational wave astronomy could finally give us a complete census revealing not just the visible giants, but the hidden multitude that shaped the cosmos from the shadows. Yet even as we anticipate these future revelations, the present discovery forces a reckoning with our observational limits. The James Webb Space Telescope detected this black hole only because of its extraordinary mass. At 400 million solar masses, its gravitational pull warped nearby gas to velocities exceeding thousands of miles per second, producing broad hydrogen emission lines that stood out against stellar noise. A black hole half that size would generate weaker signatures, easily lost in the data. Current detection thresholds for dormant black holes in the early universe sit around 100 million solar masses. Below that, they are effectively invisible. This means for every GN 10,001,830 we see, there could be dozens at 50 million and hundreds at 10 million non-detectable with current instruments, yet all contributing mass, shaping galaxies, and leaving gravitational footprints that remain unrecorded. This invisibility has profound consequences for how we reconstruct cosmic history. Every deep field image from JWST is a mosaic of light, each galaxy a beacon in the dark, but dormant black holes are the negative space between those beacons, present, powerful, and unaccounted for. Their collective gravity influences how galaxies orbit within protoclusters, how gas flows between systems, how mergers unfold. While dark matter dominates the unseen mass budget, dormant black holes could still affect local dynamics, especially in dense regions where black hole concentrations are high. More importantly, their feedback history, those past bursts of activity, would have heated gas, suppressed star formation, and altered chemical enrichment across entire protogalactic clouds. Galaxies we see today may owe their shapes, sizes, and stellar populations to black holes we never observed. And the galaxy GN 10,001,830 itself may hold further secrets. Its tiny stellar mass, just 830 million solar masses, makes the black hole's dominance all the more perplexing. One possibility is that it was once part of a much larger system, its outer stars and gas stripped away by tidal forces during a close encounter with a neighboring galaxy. The central black hole, bound tightly to the core, would remain intact, while the stellar envelope was shredded and dispersed. What we see today could be the remnant nucleus of a once massive galaxy, its black hole to star ratio artificially inflated by loss, not overgrowth. Testing this requires mapping the galaxy's dark matter halo via gravitational lensing. If the halo is unusually massive for the visible galaxy, stripping is likely. If the halo is compact and dense, direct collapse gains support. Either way, the observation challenges the dogma that black hole and galaxy masses are locked in a universal ratio from birth. Instead, the relationship is dynamic, chaotic, and context-dependent, shaped by environment, merger history, and the timing of black hole activation. Perhaps most unsettling is the implication for the universe's timeline. Standard theory assumed black holes needed billions of years to reach supermassive status. JWST has shown they can do it in less than a billion. This compression of cosmic time suggests the early universe was far more efficient at building structure than we imagined. A place where gravity operated with ruthless speed, where gas collapsed not into stars but into black holes, where feedback was not gentle regulation but violent suppression. We are not witnessing the slow maturation of a cosmic ecosystem. We are seeing its explosive birth, where monsters emerged before their cradles were fully built. And somewhere in that darkness, 13 billion light years away, the black hole sleeps. It has consumed almost nothing for 100 million years. Gas is slowly accumulating, drifting inward through gravity's pull. One day, it will cross a threshold. The accretion disk will heat, winds will erupt, the galaxy will dim as star formation halts. For 5 million years, a blink in cosmic time, it will blaze as a quasar, one of the brightest objects in the universe. Then it will fade again, returning to silence. The cycle will repeat over and over across billions of years, shaping everything around it while remaining, for most of its life, unseen. We are beginning to learn that the universe's true architects do not shout, they whisper, and thanks to a golden mirror a million miles from home, we are finally learning to listen. The discovery of this dormant black hole is not an endpoint, it's a threshold. It marks the moment humanity began seeing the universe not as it appears, but as it truly is, a domain where silence often conceals scale, where the most influential forces operate in darkness, and where cosmic giants sleep for eons before briefly awakening to reshape their surroundings. The object in galaxy GN 10,001,830, 400 million times the mass of our Sun, fasting in a galaxy barely large enough to contain it, has done more than rewrite a chapter in astrophysics. It has exposed the limits of our perception and forced a reckoning with the invisible majority that governs cosmic evolution. For decades, we built models of the universe using only what glowed. Now we know that what doesn't glow may matter more. This realization reshapes our understanding of time itself. In human terms, 100 million years is incomprehensible, an expanse so vast it dwarfs the entire history of our species. Yet for a black hole, it is a single nap between meals. The feeding frenzy lasts just 5 to 10 million years, a violent, radiant burst during which the black hole may double its mass, heat its galaxy to millions of degrees, and shut down star formation across its entire domain. Then, as radiation pressure clears the surrounding gas and the food supply runs dry, it falls silent. For the next 100 million years, it consumes almost nothing, emits almost no light, and becomes nearly undetectable. This rhythm, feast, suppress, sleep, recover, repeats across cosmic epochs, sculpting galaxies not through steady influence, but through punctuated catastrophes. And because dormancy lasts 10 to 20 times longer than activity, the universe is far quieter than it is violent. At any given moment, 95% of supermassive black holes are asleep. We have been observing the cosmos during its brief dinner hours, mistaking the luminous minority for the norm. This skewed perspective has distorted every model of galaxy evolution. Standard theory assumed that black holes and galaxies co-evolved through continuous, gentle feedback, each regulating the other in a billion-year dance of equilibrium. But the extreme mass ratio in GN 10,001,830, where the black hole accounts for 40% of the galaxy's stellar mass, 400 times the expected value, reveals that equilibrium is not universal. In the early universe, black holes could dominate their hosts from the start, growing explosively before feedback mechanisms had time to establish balance. This suggests a black hole first scenario, massive seeds formed via direct collapse of primordial gas clouds before significant star formation occurred. These seeds then acted as gravitational anchors, pulling in gas that would later form stars. The galaxy didn't shape the black hole seeded the galaxy. Over time, continued star formation and mergers would dilute the mass ratio, bringing it in line with modern values. But at 800 million years after the Big Bang, we are seeing a transitional phase, a system caught mid-formation where the architect is still larger than the structure it's building. The evidence for this lies in the galaxy's suppressed star formation. Despite existing in a gas-rich era when galaxies typically blaze with stellar birth, GN 10,001,830 forms stars at a fraction of the expected rate. Spectroscopy reveals weak ultraviolet emission from young stars, proof that star formation is occurring, but sluggishly. The culprit is almost certainly past outbursts from the central black hole. During earlier feeding frenzies, its radiation and winds would have heated the interstellar medium to millions of degrees, preventing gas from cooling and collapsing into stars. Even now, in dormancy, the gas remains hot, and star birth proceeds slowly. The galaxy is not dead, it's recovering. And this recovery phase mirrors the black hole's own state. Both are in a quiet interlude between cycles of violence and renewal. This synchronized rhythm suggests that galaxies and their black holes don't merely coexist. They breathe together, inhaling gas, exhaling energy, then resting before the next cycle begins. Detecting this hidden relationship required more than luck. It demanded a revolution in observational capability. The James Webb Space Telescope, with its 6.5-meter gold-coated mirror cooled to minus 380 degrees F behind a tennis court-sized sunshield, was uniquely suited to the task. Operating 1,000,000 miles from Earth at the L2 Lagrange point, it captures faint infrared light from the early universe, light stretched from ultraviolet by cosmic expansion and obscured by dust in optical wavelengths. Using its near-infrared spectrograph, researchers split the galaxy's light into a high-resolution spectrum, revealing hydrogen emission lines broadened by Doppler shifts from gas orbiting at thousands of miles per second. Only a supermassive black hole could produce such velocities. Crucially, the accretion disk was faint, confirming dormancy. The team cross-validated this with spatial imaging and spectral decomposition, isolating the black hole's faint signature from the brighter stellar light of the outer galaxy. Every method converged on the same conclusion: a dormant giant hidden in plain sight. Yet even JWST has limits. Its detection threshold for dormant black holes in the early universe is around 100 million solar masses. Below that, gravitational signatures are too weak to distinguish from stellar motion and thermal noise. Statistical models based on black hole mass distributions suggest that for every 400 million solar mass behemoth we see, there are dozens at 100 million and hundreds at 10 million, none detectable with current instruments, yet all shaping galaxies through past feedback. This hidden population means our cosmic maps are fundamentally incomplete. Every atlas of the early universe is built from light galaxies plotted by their stellar emission, their masses inferred from brightness. Dormant black holes contribute zero light but significant gravity. They are absent from these maps, despite potentially regulating the galaxies we do see. Imagine reconstructing Earth's climate while ignoring oceans. They don't glow, but they store heat, drive currents, and shape weather for centuries. Similarly, dormant black holes may be the hidden regulators of cosmic evolution, their past eruptions dictating where stars could form across entire protogalactic clouds. This hidden influence extends to the largest structures in the cosmos. Modern galaxy clusters, gravitationally bound systems containing hundreds or thousands of galaxies, are dominated by central giant ellipticals, each hosting a black hole weighing billions of solar masses. Simulations suggest these behemoths began as early giants, like the one JWST found. Over billions of years, repeated mergers funneled gas and smaller black holes toward the center, allowing the dominant black hole to grow through accretion and cannibalism. Its early head start mattered. A 400 million solar mass black hole at cosmic dawn would dominate merger dynamics, consolidating mass at the cluster's heart. Its feedback history, those past bursts of activity, would have heated intracluster gas, preventing excessive star formation and explaining why modern clusters contain vast reservoirs of hot X-ray emitting gas but relatively few stars. Thus, the dormant giant isn't just an oddity, it's a progenitor. It represents the seed of a future cosmic metropolis, observed during its quiet genesis. Looking forward, the next frontier is not light, but gravity itself. While electromagnetic observations reveal black holes through their interaction with matter, gravitational wave detectors, like the future LISA mission, will sense them through ripples in spacetime. From mergers, if massive black holes were common in the early universe, as JWST's findings imply, then merger rates during the first billion years were far higher than previously modeled. LISA could detect dozens of these early collisions per year, providing independent confirmation of the burst growth paradigm. Each detection would carry information about black hole masses and spins, allowing us to reconstruct the population's evolution directly. Combined with JWST's snapshots of dormant giants, gravitational wave astronomy could finally give us a complete census revealing not just the visible giants, but the hidden multitude that shaped the cosmos from the shadows. But even as we anticipate these future revelations, the present discovery forces a deeper philosophical shift. For centuries, science has equated observation with knowledge. If we couldn't see it, it didn't count. But the universe operates on its own terms, not ours. It builds monsters in the dark, lets them sleep for eons, and awakens them only briefly to reshape their surroundings. The fact that we see so few active black holes isn't evidence of their rarity, it's evidence of their nature. They are not meant to be seen most of the time, and that changes everything. It means the true architects of cosmic structure are not the brightest beacons, but the quietest shadows. It means our understanding of the universe must account not just for what is visible, but for what is inferred, modeled, and statistically inevitable. This humility is the true legacy of the dormant giant. It reminds us that discovery is not just about finding new objects, but about redefining what it means to see. We are learning to listen to gravity's whisper, to read the scars of past violence in the spectra of starlight, to recognize silence not as absence, but as concealment. And in doing so, we are beginning to map a universe far richer, stranger, and more dynamic than we ever imagined. Somewhere 13 billion light years away, the black hole sleeps. Gas drifts inward imperceptibly. One day it will cross a threshold. The disk will ignite, winds will erupt, the galaxy will dim as star formation halts. For 5 million years, a blink in cosmic time, it will blaze as a quasar, one of the brightest objects in existence. Then it will fade again, returning to silence. The cycle will repeat over and over across billions of years, shaping everything around it while remaining, for most of its life, unseen. We are finally learning to see the invisible, and in that act, we are not just expanding our knowledge, we are redefining our place in the cosmos.